Welcome. I'm Hassan, Associate Professor in the Faculty of Mechanical Engineering at Delft University of Technology. The topic of this lecture is the closed-loop control of a DC drive. The outline of this lecture is as follows. First, we will learn how to describe the dynamics of an electric drive. Second, we will study how the DC motor current is regulated with a PI current loop. Third, we will investigate how to add an extra loop to realize speed control or position tracking. After that, we will dive into the discretization of controllers, which is essential for microcontroller or FPGA-based control loop implementation. Let's first look at how the DC drive system dynamics is described. Let's look into the dynamic of DC machines as shown in the figure on the left. As discussed in the previous lectures, to simplify our analysis, the equivalent circuit of the DC motor is used. The circuit includes the armature, voltage, resistance, inductance, current, and also the back EMF, which contributes to the torque output. The electrical dynamic of the DC motor can be described using differential equations on the screen, where K times omega gives the back EMF. To make it suitable for controller design, we may convert this differential equation to Laplace domain using the Laplace transformation. In the simple word, it replaces the differential operator in front of the current with the Laplace variable s. By solving the armature current IA from the transformed equation, we can obtain the expression of the armature current in the S domain. Obviously, IA is governed by both the armature voltage and the rotational speed, and here GE represents the electrical transfer function of the RL component in the circuit. Let's continue to describe the mechanical dynamic of the DC motor. According to Newton's law, we can write the differential equation describing the rotational dynamic, where J is the moment of inertia of the rotor and the load, B is the damping coefficient. Taking Laplace transformation and transform the equation to the S domain, now the transfer function describing the mechanical dynamic is obtained. In this lecture, we will address this by GM. Equation is obtained. This equation can be described as a block diagram as shown on the slide, where GE and GM are the electrical and mechanical transfer function, respectively. Based on that, we can also write the final electromechanical system transfer function from the armature voltage to the angular speed omega, and that from the armature voltage to the angular position theta. That would be of second order and third order transfer function, respectively. Having all the involved transfer functions written down on the slide, we can see the frequency response from the armature voltage to the angular position. The Buddha plot represents a third order transfer function with a resonance frequency at RA over LA. To ensure that the motor follows the desired speed or trajectory, a feedback-based closed-loop control should be implemented. Then it comes the question, how to regulate the torque or the speed using the closed-loop control. Let's first take a close look at the torque control, which is done by the current loop because they are linearly related. Previously, we have derived the electrical system transfer function. To regulate the current or the torque, a feedback system based on a PI control with the transfer function C of S is usually used. The current loop is then described by this block diagram. The goal to design the current control loop is to let the torque T follows its reference TR. So the closed loop transfer function should approximate 1 to a certain extent. It can be guaranteed by making the open loop transfer function, which is C times GE, to be omega C by S, where omega C is the bandwidth of the current loop. Having this in mind, we can actually see how to relate the PI controller parameters to the desired bandwidth by canceling RA over LA with KI over KP. Therefore, once omega C is chosen, KP and KI can be decided based on it. By setting the KP and KI accordingly, the closed loop will behave as a first-order low-pass filter. Within the bandwidths, the output follows the reference closely as the gain is 0 dB. Meanwhile, all the high-frequency noise will be rejected. Taking a closer look at the resulted closed-loop response, we may see for sufficiently large bandwidths omega C, the reference is followed. On the top of that, we can also see that the back EMF item K times omega acts as a disturbance to such a closed-loop system and is rejected by the controller at frequencies lower than bandwidth. So when the concerned frequency is sufficiently low, we may simplify the DC motor with the closed-loop current controller as a unit gain. So only the mechanical dynamic remains. Based on the simplification above, we are able to design the speed control loop outside the current loop. We may still use a PI controller. The transfer function of it is given as Cm on the slide. Here Kpm is the proportional gain while omega Im is the targeted bandwidth. We still want the system to have a low-pass behavior as shown on the slide, where omega m is the desired speed loop bandwidth. To achieve the design target, one can see the loop gain L given by Cm times Gm should have the format of omega m over S at sufficiently low frequency. To achieve this goal, we may set omega Im as omega m and let it to be 10 times lower than the current control loop bandwidth so that previous assumption validates. Then choose the proportional gain so that it cancels the gain of the mechanical system at omega m. Looking back at the speed loop design, we can see that the assumption of the inner torque or current loop can be treated as a unity gain is crucial. This assumption is only valid when omega c is far larger than omega m. Actually, in practice, if omega m is too close to omega c, the system would become a second order and the stability and performance will be affected. So to maintain a stability, we always try to choose a sufficiently low speed loop bandwidth. The next question for us is how to realize position tracking if the application requires precision position control. The transfer function from the speed to the position is just 1 over S, an integrator. This integrator, however, brings problem to a PI controller. It introduces phase delay and will give us an improper phase margin. Therefore, a PD controller, that is to say, a proportional differential controller, has to be used to ensure stability. Now the position control loop is shown as this when a PD controller is introduced. The open loop transfer function of the position loop is given on the slide, which is a second order system. Based on that, the closed loop transfer function is also obtained. With this obtained second-order transfer function, we have to shape it to match a standard second-order response. To make them match, we can see the proportional gain KPP should match the desired bandwidth squared times the moment of inertia J, while the differential gain is matching the equation below. In practice, the rotor and load damping coefficient is often negligible. So KDP can usually be set as 2 times the desired loop damping times omega n times J. However, you may notice in the closed loop transfer function, on the numerator, there is still the differential S. It amplifies noise at high frequency. To solve this problem, we need to apply a low-pass filter to the PD controller, which results in a so-called lead compensator, where the cutoff frequency omega is usually 3 to 10 times the bandwidth omega n. The last question is how to realize these controllers in digital systems, since all previous analysis was done in frequency or Laplace domain. This is achieved by discretizing the controller by converting the Laplace domain transfer function into the discrete Z domain. A good approach is to apply the Tostin approximation by substituting S with the Z domain transfer function on the slide. Compared to other discretization methods, Tostin achieves a good trade-off between precision and computation cost. One can easily use functions given here to make the transformation. Looking back, you can see how we build up different control loops step by step using transfer functions, and at the end, how to discretize the design controller. Hereby, we conclude the lecture. Thank you for watching this video and good luck with the rest of this study.